So today we're going to cover concrete best construction practices. And this is a course that we developed from the one that we normally teach in person. And so we've modified it a little bit to fit within the time constraints for today. So just a couple of things for those of you not familiar with T-squared centers or LTAP centers in general. I know we've got people from across the country joining us today. So there's a T-squared center or LTAP center in every state. And hopefully you're all familiar with them already. But if you're not, please, get to know the one in your state. They can be a really great resource. My words, not federal highways. Our role is to reach out to transportation agencies, find out what their challenges are and help them however we can. And I think that that's probably something that most of the T-squared centers sort of follow, even if they don't think of it in those exact words. And so we do that through technology transfer, technical assistance, training workshops like this. And so if you have training and you're not seeing it in that area, talk to your T-squared center. Certainly if you're in Delaware, talk to us. If we're not bringing it, we will make our best attempts to do that. So that's sort of the quick commercial, if you will. So I'm Matt Carter, and I'll be the presenter today. Rusty Lee is with us here. He runs the T-squared center, and Sandy Wolf is here. She sort of makes sure the trains run on time for us and keeps us straight. And so again, I'm Matt Carter. My background, I'm the engineering circuit rider with the center now. I have a background with heavy construction, design consulting, and as a public works director. So I've sort of seen concrete work from the designer's perspective, actual construction perspective, and as an owner and I guess regulator, if you want to think of it in those terms. So I've seen it from the different perspectives. And hopefully I can bring some of that to bear. So today we are recording the session. Just a couple of quick navigational things. If you're not familiar with Zoom, which is our platform today, if you can remain muted, just to keep any background noise out when you're not speaking. You can keep your video on or off. It's your choice. We'll do just a couple of polls. We're not real poll happy, but just a couple of things to get a little bit of feedback from you. You'll see a banner. You may have to pull your cursor down to the bottom of the screen to see that black bar. It's not always black, I guess, but in any event, it's a bar like this. And you'll see things there with the chat pod, for example, and reactions and things like that. So for example, you have these reactions that they're all positive, mind you. So, but you can use those and you can certainly put things in the chat pod. So, we encourage that you do so. As we go along, if you have questions or input, absolutely put them in the chat pod. Sandy and Rusty are going to help monitor that for me. Again, I have a certain experience and perspective and knowledge about this, but I suspect that with a number of people here, there's lots of people that have very different experience and knowledge. And so by all means, speak up, particularly if you think at some point that I've gone off the rails a bit or am speaking from which I don't know. So don't be afraid to sort of challenge me with that, and we'll talk about it a little bit. So let's jump in. So we're going to have a focus today on concrete flat work. A lot of what we'll talk about applies very much to concrete work in general, including things like, pouring bridge abutments or head walls or, any of the things that we might do, foundations and so forth. But we're going to sort of gear this towards flat work. And by flat work, we mean those things such as sidewalk, curb ramps, curbing itself, and so forth. And we're also going to be focusing on exterior concrete. There's a handful of things. I'll probably touch on them here and there as we go through that are a little bit different with interior concrete, but we're going to focus on exterior concrete today and flat work. So you know, all of us have all kinds of flat work in our jurisdiction of various sorts. And a lot of us have some that has been there for a long time and, you know, decades even, and still looks pretty good. And we have some that, you know, is relatively new, and you wonder what in the heck's going on with it. And, you know, I think that we agree that if we properly construct concrete, we should get certainly a 20, 25, maybe 30-year life out of it pretty comfortably. Certainly, we know lots of concrete sidewalk and other kinds of things that have been around for the ages, and it certainly might show its wear, but it's still hanging in there fine. So we ought to be able to replicate that. But we've had problems. And so just in Delaware alone, you know, I mean, we certainly have had a lot of issues with poorly performing flat work, but it's not unique to Delaware. Again, just to use an example, you know, in Montgomery County, Maryland, they did a few years back, they did an $8 million sidewalk project, and it started showing significant deterioration just in the first few years. And it made the Washington Post, which is not what you want your project to generally do, unless it's a ribbon cutting. And the public pretty well wigged out. They didn't like that. They thought it was incompetence. They got pretty upset, and they probably had some good reason to do so, because that, you know, that was not a reasonable expectation. So the problem that, you know, the big problems that they saw there, and that are pretty common to a lot of our flat work, can look like this. It can take on some other forms, but we get some form of scaling or pitting, or mortar flaking, or that type of thing. And this is just the beginning of the problem, right? When we see this early on, we know that further deterioration is headed our way. So we kind of have three different categories. Again, the difference in terminology starts to meld a little bit, but we have scaling where we start to lose that surface, usually because it's a weak paste, and we'll talk a lot about that. We can get mortar flaking where we don't have good bonding between the aggregate in the concrete and the surface mortar, and that flakes off. And then we can also get pop outs. And these things can happen. We can see these manifest themselves in a given project together or separately. It varies a good bit, but all of it leads to further deterioration, and certainly not the kind of look that people are expecting. And so scaling, which, you know, we'll put a lot of focus on today, can come from a lot of different pathways. Certainly excessive finishing, and we'll talk about that. Anytime that we get excess water into the mix beyond what is needed, particularly if we're working bleed water or, you know, into the surface, or blessing the concrete, or that type of thing. It can also result because of too little air entrainment, where we've knocked the air out of the mix, and we'll talk specifically about that. Certainly insufficient curing, particularly when we get into the extremes of temperatures. And de-icing materials can be an issue, but we'll talk about that a little bit as well. You know, when we have materials like this, where we start to see that we're losing the surface of the material, it's not going to get better, and we can reasonably expect that it's going to deteriorate more, and the public is not going to be happy with us. So here in Delaware, you know, the Delaware Department of Transportation in particular, and some of the local agencies increasingly were frustrated with results. They looked into research, you know, or mixed design research, did a lot of different things, and amongst other things, modified their contract specifications. And so, you know, they put this specifically into several sections of their standard specifications, where they said that a certified concrete flat work technician would have to supervise all finishing. And that proof of that certification would have to be evident to the inspector on the job. And that was done going back about 4 years ago. And so let me do the first poll question and ask whether you all have, oh, I don't have it. Because of my earlier confusion, I don't have it in this meeting. So let me get you to put into the chat box. This is a good thing to put into the chat box. You know, do you require a flatwork certification in your area or in your agency? Is it in your specifications? You know, yes, no, or, you know, that you think perhaps you will going forward. So if you can throw that in, I'll move on, but it'll be interesting to see the results. We'll check back on that in just a moment. So let's talk about how we can go about. Let's talk about those best practices so that we can avoid, you know, the problems. So when we're placing concrete, you know, we start out with the forms themselves and the sub base that we're building the materials on. We certainly want clean, you know, forms that are in good condition. We want to place it on, typically we'd like to place it on some kind of a stone, whether it's graded aggregate base course or some other material. That's not always necessary depending on the kinds of materials that are indigenous to your area. But pretty commonly we like to do that. You know, we want release agents, that type of thing. We want to pay good attention to expansion joints and control joints and that type of thing, which again, we'll touch on some of that in a little while. When we're placing concrete, we have to be very mindful of temperature extremes. So in cold weather, and again, some specifications vary. And certainly there are means by which you can place concrete in colder temperatures, but then you have to take some pretty extreme measures to do that. Similarly, in hot temperatures, we need to be really mindful of the plastic concrete and how that's going to affect, in fact, cold weather, we have just the opposite problems with bleed water and things like that. So we'll come back to that in a little bit, but we really want to watch those extremes in temperatures because we may have to take some measures.
Okay.
Bob, can you mute that for me? Thank you. You know, we'll have to, as we approach those extremes in temperature, we'll have to take some measures to make sure we don't get in trouble. And there's just a point at which, you know, when it's, you know, it's particularly cold or particularly hot that we may have to suspend altogether. In terms of finishing concrete, you know, there's a handful of sort of basic things. We want to, you know, first of all, just the placement of the concrete itself. You know, we would like, not much like with some other materials that we have, similar to asphalt in some ways, we'd like to place that material in as close to where we're going to finish it as possible. The more we move material around, and sometimes it's unavoidable, right? If we're working in some tight spots, we may have to use a shuttle buggy or a wheelbarrow or something else to move batches of material in. But the more that we can take it right out of the truck and deliver it in the direct vicinity of where we want to finish it, the better off we'll be in terms of avoiding segregation of the material. We want to get good consolidation by vibration and other means. Strike it off. Typically, if we're dealing with external concrete, we want to use either a mag float or a wooden float. And then we really want to wait until that bleed water comes off. And we'll talk about that some more as we go along. You know, and again, thinking in terms of extremes, in much warmer temperatures, this process can happen fairly quickly. And it can be actually hard to tell whether you're getting bleed water off. In cold temperatures, it can take an exceedingly long time for that bleed water to make its way to the surface. So we really, there's a bit of an art and craft involved in this and sort of reading the personality of the concrete. You know, again, once we have waited for, you know, either removed the bleed water or allowed it to evaporate, then we want to go about the, you know, the process of finishing the surface. So we see some examples here. This is actually from, these are pictures from a certification course that's being used in Delaware. And so these are actual inspectors and concrete finishers going through the course and doing, you know, the course practical. And so they set up certain, you know, they set up test beds at a ready mix plant and pour the concrete, finish the concrete, cure the concrete, and sort of learn some of these best practices in a very hands-on way. It's a really great way to go because particularly for inspectors who, you know, maybe have never actually finished concrete, and this, you know, gets them a little bit of hands-on experience so that they can better appreciate how difficult it is sometimes, not only to do the work, but also sort of read the conditions properly. You know, a lot of what we see here are pretty good practices. They're not always the best practices in here. And again, particularly in the lower left, you see where, you know, an inspector who's not used to cutting joints gets a little bit of lesson as to, you know, experienced concrete finishers make this look easy. When you put that joining tool down in there and, you know, run into all that aggregate and realize that that's a skill that you have to develop over time. So again, it gives people an appreciation for this. And again, that certification course goes all the way through properly brooming and curing the concrete as well, which again, we're going to touch on those best practices as we go. Here's actually a project that I observed while I think this was in Indianapolis a couple of years ago. And, you know, this is a fairly typical thing you can see in an urban environment where you're working in some pretty constrained places. And there's a lot of joint work that's necessary, and then a lot of joint work that gets added in for aesthetics purpose. And that excessive joint work for aesthetics can have a weakening effect on the surface as well, because there's a lot of excess finishing that goes on to make that happen. It's not the fault of the guys trying to put this stuff down. They're just doing what the plans required. So let's talk about those joints. Concrete joints are sometimes misunderstood. You know, if the picture on the right, I distinctly remember I took when we were out on the US 301 project in Delaware when that toll highway was being constructed a couple of years ago. And you know, our center had several interns embedded in the project to film it for training purposes. And when they saw this, they said, "Oh, that must be a problem." And I said, "No, that's exactly what we want to have happen." And I said, you know, that's why we cut a control joint, because concrete is going to crack no matter what we do. It's in its nature. And so what we want to do is try to exercise some control over that. And control joints is part of how we do that. And so understanding that is important so that we then do a better job at placing and cutting those, either cutting or forming those control joints. Basically, we're instructing the concrete, we're giving it a relief location so that it can crack where we want to, instead of very irregular, sort of sporadic cracks. A construction joint, on the other hand, is typically takes its form in something like this, where it's the end of a day's work, and we form off the end of the project so that we can then remove that and continue on another day. They won't all look like this. They won't all have continuation bars necessarily. In this case, we do have it. Curing concrete. So there's lots of ways to cure concrete. The idea is to keep the needed water in the mix while it needs it for hydration, and control that process. We can do that by the method we see here, where we've got wet burlap that we keep wetted down on the surface. We can do that with sheeting. We oftentimes we'll do that as colder weather sets in, and even use thermal blankets on top of that. And we can certainly use curing compound, which is pretty common. Another concept or myth that you run across with curing compound is sort of a making of our own jargon that we use in the field. A lot of times a well-intended phrase is uttered to the person applying the curing compound to encourage them to put enough material on the surface to be effective, and they'll say, paint it white. Well, the problem is that when they don't know any better, they come to the conclusion that the purpose of the curing compound is aesthetics, that we're somehow painting the surface. I actually heard an inspector say this during one of the certification runs that we were running in Delaware a couple of years ago. They said, well, but we wouldn't need to do it with this plant because their mix already comes out pretty close to white anyway. And the instructor, stopped and did a good job. He didn't embarrass the guy, and that, it's a misunderstanding. And he said, yeah, that's not why we're using this. This is a sort of waxy material, or dries as a waxy material on the surface. And the idea is to seal off the surface so that you don't get uneven drying in the concrete as it cures. We want to be mindful of using the correct compound. And the correct compound is usually a function of what your specifications are. Somebody's going to great lengths to specify a particular sealant material or range of sealant materials or material properties about it. And we should make sure that the contractor is using that material. A lot of times we'll have a very specific specification like we see here. And when you actually investigate the material that's being used, it doesn't comply with that. Now, that doesn't mean that it's not good material. It's just not what was specified. So if we've gone to all the trouble to specify this, we want to make sure we're using the right material. And if indeed other materials are adequate, then we should, over time, modify our specifications to allow that. Again, this notion of painting it white, our point there is that we want good coverage, and we want to get enough of the curing compound on the surface to do its job. Much like we would for some other coatings, oftentimes doing it in two directions is a good way to affect that. And we really want to get curing compound, or if we're using other curing methods, on the surface as soon as we can, as soon after finishing and brooming the concrete as we can. So, whether we're using curing compound, whether we're using wet burlap, et cetera, we really want to get in there as soon as possible right after. We don't want to delay that because literally minutes can count, particularly when you're in hot weather. Another best practice is avoid the wrong concrete, right? We've got to get the right mix. And that starts by choosing the right mix. But it also goes to making sure that the mix that's delivered is what we asked for, what we paid for, what we specified. There are all kinds of additives, admixtures, et cetera, accelerators and things like that, some of which we'll talk about in here. And if those are part of the mix design and are required to be there, then we want to make sure that the delivery tickets reflect that and we've got the right material. We want to pay really, really close attention to adding water, whether that's through the use of brushes and so-called blessing of the concrete, or whether that's arbitrarily adding water to the mix in the truck. Excuse me. And we'll talk more about why that can be such a problem. So the right mix design is what was designed, right? What was specified. And a lot of times, particularly for public work, we already have established mix designs for particular kinds of work. We should never assume that from job to job. We should always look and ensure that, in fact, it hasn't been modified in some way, but we really want to make sure that we're using the right material. And typically we'll see certain things in there, like you see in this table, where you see that mix B, which is a typical mix that we would use for something like roadway, is going to have a water to cement ratio as a maximum. We'll talk more about that. An air content ratio, we'll talk more about that. Most of us are already familiar with the strength, the 28-day compressive strength of the concrete. And, you know, we may have other things like permeability in there. And those are all very specific to what we're trying to achieve with a particular pour. So let's talk about this notion of water to cement ratio. So within limits, the lower we can keep the ratio of water to the actual cement in the concrete, the higher our strength and durability will get. Now, there's obviously minimums to that. And it's helpful to think of that in terms of what's going on with concrete. You know, concrete is, of course, a mix of several materials: water, the cement itself, fine aggregate, other things that we may have in it. And we're counting on this process of hydration. It's a chemical reaction where all of these materials harden together through that chemical reaction. Well, that requires about 0.35 pounds of water per pound of cement. And that's why it's important for us at some point to know, well, how much cement is in the mix? What is the mix? Because that dictates how much water needs to be in it, and then some upper limits of beyond which we don't want to add water. So a 0.35 water to cement ratio would suffice. And that works pretty well in a laboratory setting where we can control everything. But we know that indeed, we don't have that much control, that much homogeneity, et cetera. So we typically move that up a little bit. And so something like 0.45 is pretty common for a lot of mixes. We will sometimes go up as high as 0.55 or 0.6. But that's sort of the upper end of the range. Beyond that, you've given the concrete way too much water for what it needs, and you're going to weaken the concrete as a result. And so, you know, if we get a excessively watery mix, it leads to segregation issues. It's going to weaken particularly the surface material. We're going to get shrinkage. All of these things will come into play. And so we really want to make sure we're in that range. And with a little bit of care, it's not that hard to do that. And we'll talk about some of those as we go. You know, very understandably, if you are a concrete finisher, if you're the foreman on that job, you would like a creamier mix. You would like a mix that's easier to move around a little bit, to float the surface, and to ultimately finish the surface. That's understandable, and that's achievable without adding excess water to the mix. Pretty commonly, you'll be on a job site, the concrete truck backs up, the chutes go down, and before the material is even floating down the chute, the foreman will say, add 10 gallons to it. That's a terrible practice. He hasn't even seen that mix yet. And we at least ought to look at it and see whether it's going to work for us. You do need to add water sometimes to the job site, and there's a proper way to do that, and there's proper limits on that. But we should avoid doing that until we need to do that. You absolutely can add water. There's an allowance in most mix designs, and there's a way to actually mix that water in properly. If we have in our specification, a maximum water to cement ratio like 0.45 or 0.5, something like that. They can go up to that. And the mix design should tell us how much total water we can put in. And the batch plant should be advising us on the on the truck tickets, how much water is, quote, been held back. In other words, how much can they reasonably put in? What are their limits in terms of putting material in the field and still be within spec? We should not allow the contractor, the finisher, to be adding water to the surface as we go. And there's not 100 tricks, there's not 1,000 tricks, but there's certainly dozens of tricks. The most obvious, of course, is sloshing water on the surface with a cleaning brush, so-called blessing of the concrete. When we stop that, suddenly they've got a water bottle that's never drunk from, that has a hole in the lid, that's being used for the same purpose. Ridiculous frequency of washing the tools to bring more water onto the mix. And we simply just shouldn't allow this. If we got the right mix to begin with, we shouldn't need that excess water on the surface. If we're going to add water, we should do it the right way. We do it in the truck. And again, this is an excerpt that I won't go through, but this comes directly from the American Society of Testing Materials and their standards for ready mix concrete. And it talks about, first of all, that we don't exceed the maximum water content for that batch. And as inspectors, as owners of projects, we should insist upon adherence to that. If we do that, again, it continues on. It tells us how we do that. We do that before we discharge any material from the concrete. Because again, if you did it a third of the way through the load and you're adding the amount of water that was, quote, held back, maybe 10 gallons was held back, 15 gallons was held back, then you're adding too much because that was intended for the full load. So you do it at the beginning of the project or you don't do it all. And then once you do, we need to turn that mixing drum at least 30 revolutions at the proper mixing speed so that we get full homogenization of that material. And we really, as project owners, we should insist upon those proper practices if we are indeed going to add water at the job site. Let's talk about salt, shifting gears a little bit. People say, well, scaling happened because, you guys use salt. Well, yeah, we all use salt. I mean, unless you're in Texas or Florida or someplace like that. But, in the mid-Atlantic and certainly in the snow belt, we use salt. Properly constructed concrete should be able to hold up to reasonable applications of rock salt, of road salt. Get into that more later on about where, we can run into some problems with that. But if we follow those best practices, we have the proper mix, it's actually created correctly and it's batched properly, and we're careful about bleed water and we avoid steel trowels, which I'll talk about more in a moment, over finishing and things like that, then we ought to have a concrete that's durable enough to withstand a reasonable application of rock salt. But we have to use those best practices. And so, if I counter with that, a lot of times folks will say, yeah, but we use a lot of rock salt. And to which I say, well, stop that, right? Why do you want to waste money? If you're using more road salt than is necessary to achieve your winter maintenance goals, then you need to examine your practices with that, because there's probably, we know across the country that lots and lots of agencies have used better and better strategies, not just the use of brines, but other strategies to minimize their use of salt and still get good results for winter maintenance. So we don't have to use excessive amounts of rock salt. Second, well, we use magnesium chloride in our mix, or calcium chloride. There's nothing wrong with that. That's fine. We should just think in terms, we should know what's, how much of that are in those materials. Even if they're proprietary blends, we should try to find that out, and we should be a little bit frugal about it. We talk about that more in our winter maintenance course. If you missed it, we just finished that online last week. but it is on our website. If Sandy or Rusty can find the link for that and want to drop it in the chat box for anybody that wants to go and see the recordings of those. We talk some more about that in that course. So let's shift gear to slump a little bit. So, because this was referenced before in a couple of slides. And so, you know, most of us are probably familiar with the notion of slump and how we measure it. First of all, you know, and again, it's a measure of the consistency of the concrete and the workability of that concrete. If we, and obviously, you know, the example you see on the left has a lower slump, looks like maybe a 2.5, 3 inch slump, something like that. And so that's consistent with what we would typically shoot for. The one on the right has a very excessive slump. It looks like more like, you know, 8 or 9 inches, maybe something like that. That's a pretty soupy mix. And we'll talk about some of the effects of that. We don't have to have a soupy, slumpy mix like on the right just to be able to effectively finish it. There are other things that we can do, and we'll talk about some of those. When we measure slump, we should do it correctly. That goes to any of the tests we use. There's just no point in, if we're going to go and buy a slump cone, you know, kit, if we're not going to actually put the material in correctly into the cone, if we're not going to use the correct rod that comes with it, that's specified in AASHTO T119, and rod the correct number of times, then we're not going to get consistent results. And testing depends upon consistent applications. Otherwise, we have no confidence in what those results are. So we shouldn't phone it in. We should make sure that we're following those procedures to the letter every time, even with things like thermometers. I mean, thermometers are cheap. You know, we don't need some high grade thermometer, but we do need to use it properly. We need to put it in the material. We need to correctly in correct location, and we need to wait for a proper reading and so forth. The correct slump, well, it depends on the nature of what we're pouring. When we're talking about you know, if we're talking about sidewalk and things like that, DelDOT, which is not terribly atypical of other state agencies, is shooting for a 1 to 3 inch slump. So a fairly tight mix. The problem is that a lot of finishers will see that kind of a tight mix and immediately want to add water to it because they feel like they can't get a good finish. And let's face facts, if you're a concrete finisher, you're a craftsman, not unlike other craftsmen. If you're a plumber and you're sweating pipes, you want those pipes to look nice when you're done, even if, quote, nobody's ever going to see them. Well, you saw them, and you take pride in what you do. And finishers are the same way. When they're done finishing sidewalk or a roadway or curbing, they want it to look nice. That's understandable. But if it looks nice at the expense of being durable, then that's absolutely the wrong priority. The reality is we can get both. And the contractor can order a creamier mix with that fairly tight slump by using things like super plasticizers, and that avoids exceeding the water to cement ratio. We hear about slag and fly ash and other kinds of materials that are added to it. So let's just talk about what those are. These are used typically, amongst other things, to reduce cement content in the mix, which oftentimes saves money. That's sort of the driver. It can help with so-called alkali silica reactions, which probably many of you are familiar with. We had a big problem with it here in the Mid-Atlantic for a number of years until we got a handle on it. And we do much better with that now. But that's a very destructive sort of interaction between the aggregate and the cement that if we don't know how to look for it, can give us some real failures relatively early in the life. Again, we know a lot more about it than we did 30 years ago. So we do well with it now. We know how to look for it. But we can have these kinds of problems. And so slag and fly ash sometimes are added to the mix to help with those issues. It will, like any kind of additive, it's going to change the nature of the mix, right? So these oftentimes don't react as quickly as the cement itself does. And so we may have a longer period before we start to see, for example, the compressive strengths to go up. That's not necessarily a problem, but we want to be mindful of that in, for example, in very cold weather where we're pouring concrete and we know that we need to get concrete to at least about 500 PSI before it can freeze. And so if we've added a lot of these materials that has slowed that, we could end up in a problem. So we want to think about the temperature conditions, the environmental conditions in terms of our mix design, if we're going to add these kinds of materials. Air entrainment is another factor that I alluded to earlier. So, these are, they're tiny bubbles, right? They're bubbles that are intentionally intended to get in the mix. This is something we very much want in external concrete. In interior concrete, if you were doing, for example, a warehouse floor in an enclosed climate-controlled building, you might you're not as interested about this. Why is that? Well, because the bubbles, the reason we want air entrained in our concrete for external concrete is that we want to fight against freeze thaw, right? We want to give places for the water that's still in the concrete to go and hide out, because the air in those spaces are compressible, whereas the concrete will just crack, but the air in there will compress, and so that water has a place to go and hide. And so air entrainment is very important for us. And again, you'll typically see that specified in most mix designs. We measure that by putting it, again, there's all kinds of ways that you can do that, but this is the most common way we'll see it is with an air content meter. This is, whereas a slump cone is a fairly inexpensive piece of apparatus to buy, maybe $150, $175, $200 for a kit. These can run more in the arena of $1,200, $1,500, $1,800. And this is, I believe, the classical version of that. There's a newer version. It's a little bit more of an advanced test, and those obviously cost more. But again, if we want good results, consistent results, we've got to make sure that we use this equipment. First of all, this piece of equipment has to be calibrated periodically, depending on how much use and how much care it's gotten, to make sure that it is indeed accurate. We've got to make sure we put the mix in accordance with the test standards. We've got to do it all the right way, or our results are not going to be dependable. So let me ask, if you could put in because I don't have the poll question in this session, otherwise I'd put this up and we could do it automatically. Which of these do you perform? Do you, with whether you do it or you have a consultant that comes in and does it, or you require it of your contractor to do with your oversight? Do you use slump? Do you use air content, temperature? Do you do none of these, or does it vary quite a bit? So if you can put that in the chat pod, and we'll come back and look at that a little bit. So while you do that, I'll move on to time. Concrete cures technically inevitably or indefinitely. So for example, the concrete in the Hoover Dam is still curing. But the bulk of it happens within about a month, 28 days, right? We pretty much become asymptotic to the compressive strength that we're going to see with that. We're not going to get much after that with most mixed designs in most environments. But more importantly, even at the very beginning stage, once the concrete is made at the batch plant, the clock starts ticking. And so specifications will vary a little bit from owner to owner agency on this, but most of them reflect what the American Concrete Institute has found to be wise. And these are, that Del use are pretty typical kind of timeframes where, generally, less than 90 minutes from the time that it's produced at the plant to the time when it's placed. And so that, just like, for example, with asphalt, this requires that the contractor do some pretty good advanced planning. I mean, if you are 30 minutes from the batch plant, well, then, you can do the math about what amount of time you have to get it placed. When you get out off of the mid-Atlantic, it's not unusual to be considerably larger times from it. And so you've really got to take this in consideration and think about what you're going to do about the time lag between when it's produced and when it's placed. And again, Del limits that a lot closer. We're a small state. It's hard to get too far from one of our batch plants. So that works out pretty well. In terms of, we want to be a good customer with our concrete. And so when the concrete truck, first of all, even before we're doing the pour, we ought to be communicating with the batch plants, making sure that they understand what our expectations are, and whether we do that directly or whether we do that through our contractor, whatever the relationship is, we want to make sure that that they understand that we're going to be paying attention, that we want to make sure that we get the mix that we asked for, the mix that we paid for, and that we're, outside of whatever tolerances we have, we're not going to accept something other than that. And that just comes down to being a good consumer. The truck ticket itself should have, in accordance with the ASTM standards, a substantial amount of information just as a base. And so those are laid out here. I should also go back and say, I failed to say at the beginning of this, and Rusty and Sandy, if you can drop the link to our website where these are as well in the chat box so people have it. All of these slides are available to you on our website as a PDF in full size. And so, certainly go back and use those for reference as well, because some of these I'll go through fairly quickly. But this is the kind of information that's required to be on the truck ticket. And it continues on. In addition to sort of some of that basic information that we see here, we also get into, all right, truck going by, the class of concrete, the amount that's there, the timings, right? So if I'm an inspector and I know that our specification allows only 60 minutes until it's placed, well, I want to know when it was mixed, because I'm not interested about when the truck arrived on site. I want to look at the truck ticket and know that, well, he's been on the road for 25 minutes. This mix is 25 minutes old when he rolled up on the site. So I want to see that on my truck tickets. And so all of this information, is required to be on there in accordance. If your project adheres to the ASTM specifications, which is pretty common, then all of this information is supposed to be on the truck ticket. There's additional information that can be on there that you can require to be on there. Again, some of this is, driven by the kind of mix design you have. So if you have things like, pozzolans and fly ash and that type of thing, then your specifications ought to be clear that needs to be reflected on there, because that's the batch plant saying the stuff that you asked for is in this mix. I'm certifying to it. You can be sure that the right mix rolled out on your job. One of the things, moving on to some other best practices, one of the things that we often see in external concrete is we'll put plastic or some other vapor barrier down underneath, for example, a run of sidewalk. Generally, we don't want to do that, and there may be exceptions to that rule, but that's something that we're actually looking for more commonly in interior concrete. And the reason for that is, you know, if it's working like it was intended to do, it's going to be a vapor barrier, and it's not, and so bleed water can't leave the concrete and go down. It's going to pull at the bottom of that material and make the sort of, you know, underbelly of our concrete slab or whatever it is weaker than the rest of the material. We would like that bleed water to be able to go down into the stone and leave the mix because it's excess water. That's the nature of what it is. We'd also like to, you know, we want to avoid, you know, we want to use the proper materials to move the concrete around. We want to use so-called come-alongs like we see here, or flat-bladed shovels. You don't want to use garden rakes, pointed shovels and things like that, because what we find is that creates a lot of segregation in the mix. So we really want to use those right tools because segregation is an enemy for us in concrete, just like it can be in asphalt. We also want to avoid steel trowels. Now, on interior concrete, that's usually not an issue. Why the difference? Well, because steel trowels will remove air entrainment from our mix. So interior concrete, we're typically not using air entrainment. We're not relying on that. But in exterior concrete, we're relying on those bubbles in the concrete to avoid shrinkage and cracking and things like that. And steel trowels, as opposed to wood floats, mag floats, those kinds of things, will remove air entrainment from the mix. We would, along those same lines, we would like to delay any of the edging and joining of the surface or the mix. I'm going to wait here until a truck passes. Give me just a second. We'd like to delay that until the bleed water has passed from the mix. And the reason for that is that most of our edging tools and joining tools and things like that are in fact steel tools. And they're going to have that same effect of removing air from the mix. And it's going to do it at the worst possible places, right? It's going to do it at that edge of the concrete where the most abuse to that slab, say a concrete or a curb or something like that, is going to occur, where there are things bumping into it, running up over it, etc. It's the last place we want to lose that durability. So it's not always possible. Usually it is. We would very much like to encourage people to delay edging and joining until after the bleed water's left. Joint depths, again, for them to be effective, they need to be a quarter of the thickness of the slab. And we want to use the right joining tool. So for example, you often see that somebody is using, say, they're pouring, say, a 6-inch sidewalk slab, but they're using a 1/4-inch joining tool. Well, that's less than 1/4 of the slab. So they're not getting the proper depth for that slab thickness. And so we really should insist that they go, and in that case, probably use a 3/4 inch. If my math is right, I'm an engineer, so I can't do math, but I'm pretty sure that's right. Use a 3/4 inch joining tool. Or no, that'd be, I'm sorry. See, I am bad at math. So we would want much more than that. We'd want like a 1 1/4 inch if we were doing a 6-inch, or we would want to cut the slab. Again, there's other methods we can use. Pattern concrete has become very common. It's called for in a lot of particularly urban areas, streetscapes and things like that. The problem is it's form over function. And I'm sure that, that it's very aesthetic and makes a big difference. But the problem is that as we put those, you know, as we're working that concrete, we're overworking the surface. Now there's ways that we can do that. Stamped concrete doesn't have the same problems. So if we really do insist on that, then we can take methods like stamped concrete that don't overwork the surface to the same degree. But again, in that, similar to that Indianapolis example I showed you towards the beginning of this, where there were just all of these excessive joints, they were there for aesthetics, not to control the cracking of the concrete. And they're going to pay a price with that in concrete that isn't as durable over the years as it could be. So I've come back to that. So here's an example. And again, you can't blame the people on the job site. They're doing what they were told, but you can just see how much they're working that surface in order to get the finished product and have it still look attractive. They're spending way too much time floating that surface, and they're running steel tools along to get those joints way too much as a function of the square, you know, the surface area of the concrete. And it's a poor practice, and it should be avoided early on in the process when we're designing the job. So if we were in a live class and had a little bit more time, I might play this video for you. It's about 18 minutes long. We're not going to do that today, but I really would encourage you, again, access the slides from our website and click on this link when you get a chance. It runs about 18 minutes, and it's a little bit old. It's from the Portland Cement Association. So it's probably 20 years old or so, but it's still very valid. And it's worth viewing. I'm going to go through the sort of salient points of that over the next probably 20 slides fairly quickly, because some of this I've already talked about a little bit, but I just sort of, you know, so you'll get a flavor of what they talk about. Excuse me, but they have some really good visuals in that if you get caught up a little bit with some of the jargon or something like that I accidentally skip over, you'll see that a little bit better in that video. So the first thing they talk about is, well, what is the material? What is concrete? And again, we have a bad habit sometimes of using the term cement and concrete interchangeably. And that's a mistake because cement is a component of concrete. Concrete is, you know, an amalgam of materials that we put together. And, you know, so these are the typical ones here where you would have water, cement, and, you know, smaller aggregate and sand, but also some of those additives I've talked about, like fly ash, slag, super plasticizers, things like that. But that's the basic material, and the cement and the water form this paste or glue that holds everything together. And the process depends on that hydration, the hydration process that I talked about earlier. That's a chemical process. We know it's a chemical process by the fact that if you've ever poured concrete, particularly in the winter, you'll notice that, Wayne, can you,
this is what I shared with you.
Wayne, can you mute there? There you go. Thank you. You know, after a period of time, and again, it changes a little bit with the mix and with the weather, but a substantial amount of heat will come off of that surface. Concrete generates a lot of heat through the process of hydration. So, you know, the purpose that we have in mind, you know, we shouldn't pour a 9,000 PSI concrete mix for most sidewalk. Now, there's exceptions. If we were going to be running heavy traffic over it, really heavy traffic, we might want that. But that would be pretty rare, right? So we typically are using a 3,000 pound mix or something like that for those types of things. But there are all kinds of other elements that we're looking for. Again, if we're doing internal concrete, we're probably not going to do air entrainment, whereas with external concrete, almost always would we do that. Water. So you know, it really is the three bears scenario, right? If we have too little, we're not going to complete the hydration process and not properly cure the concrete. If we have too much, it just isn't going to be able to bleed out of the mix, and we're going to have a lot of excess water, and we're going to have weakened concrete, less durable concrete. We really want the mix to be very homogeneous. We want to make sure that all of the aggregate that's in the material is properly coated and that everything is evenly distributed in there. That's part of what makes a mix more workable. Again, too little is a problem, too much is a problem. So if we go to the extreme edge where we shouldn't, of having too little water in the mix, combined with the lack of other best practices where, so for example, this picture might not be a case of too little water. It could be that we didn't properly consolidate the concrete in the forms. In fact, if I had to bet, I'd more likely bet on that, but I don't know. So we've got to, we can't focus on just one best practice. We really have to deliver on all of them. As we said before, within reason, as long as we have the minimum amount we need, less is better. We want to run good slump tests. We want to know what it is that we're working with. And if we do add water, we want to make sure that we do it correctly. And again, referencing back to the ASTM standards for that. We can place concrete in a lot of different ways. We can have fixed forms. We can have slip form pavers. Again, part of that drives what we'd like to do. Certainly when we're doing slip form paving, whether that's a curb machine or a roadway slip form paver, we particularly are looking for a very, very low slump because we want to move at a relatively brisk pace and we want the material to stay right where it is. You want to go to the extreme of that, go on YouTube or some other source and look at some of the videos from concrete pipe production plants like Rinker and places like that. And they will show you that they're using a zero slump mix because they literally put this mix in the forms, in these vertical forms. And as soon as they've run consolidation shakers for that, literally in under a minute, those forms are pulled off. And that pipe is, you got a 20-foot section of pipe standing up on its bell on the platform floor, and they move it along and it's fine. So, you can, when you've got that real low slump, you can very much minimize your time in the forms. On the other hand, when you have things like tight rebar cages, which, think about if you're doing, even a bridge deck, depending on its design, can have a fair amount of steel in it and can be a challenge. But that's pretty common. We sort of know how to do that pretty well. But, think about, for example, what happens oftentimes where we've got a parapet for a bridge, the barrier wall, and, we've got all of this steel requirement to make it crash worthy. But then somebody decides that they're going to put 3 runs of conduit in it. Well, now that rebar has to be pushed around. You may have some bar a little tighter than others. And so to get that material in there and get it properly distributed and properly consolidated can be challenging. So, but there again, as opposed to wanting a sloppier mix, what we'd like to use is a water reducer. So we still get a good durable mix without having to sacrifice. And if we're doing road patches, we would oftentimes add other chemicals that would give us high early strength. It's not uncommon if you're doing patches, you might want to open up the lane you worked on that evening. So you would finish pouring. I did a lot of this early on in my career, where we would pull patches starting at 6 in the morning until noon, and then we would stop, and 6 hours later we would get a break. We would cover all that with wet burlap and plastic and thermal blankets. We'd have to stop traffic in both directions because when we pulled the blankets off, the amount of steam took visibility to zero because there was so much heat in this concrete. So there you were using very specialized mixes that would give you a very early on high strength without necessarily sacrificing durability. It's costly, but so there's, again, we want to match the mix and the approach to the job to what it is that we're trying to accomplish with the project. Most of the time how we place concrete is fairly straightforward. When we're doing sidewalk, even bridge decks like we see on the lower right, nothing terribly unusual about that other than just being mindful of doing it all the right way. But sometimes if we're pouring retaining walls or head walls or things like that, those may be very tall, like in the one on the upper right, and we'll use what are commonly referred to as elephant trunks, because we don't want to take and drop concrete 12 or 13 feet down, because as it rocks down through all of that rebar, it's going to cause a great deal of segregation, and we're not going to get a good durable construction when we're done. So we want to be mindful of what it is that we're building and make sure we're using the proper placement techniques. Again, in that video, they talk about colder and hotter temperatures. I won't go through that again. We want to be mindful, again, at the extremes of the years in particular, with what humidity can do to us, what winds can do. So perhaps it's, a borderline cold day, but the winds are high. Well, or let's say it's a particularly hot day and we're already concerned about the concrete drying out quickly before we can get the bleed water off. And, we've got winds on top of that, which may exacerbate our problems. So we really want to think about all of those weather conditions as we're proceeding. If we have cold climates, again, we have those other concerns that we have to be mindful of. So again, we talked about air entrainment. And again, that's essential for us in external concrete, because we really have to be mindful of the impacts of that freeze thaw, and air entrainment is a huge tool. Once we get it in the material, we want to make sure we don't beat it out of it through excessive finishing or using steel trowels or things like that. They also go through in the video the types of cement. And again, this is fairly straightforward. We will typically use, type 1, type 2. You get into these A modifiers, and those are the ones that we're going to see, right? We're going to see that A addition with a lot of our external concrete, because that's got added air entrainment. And so that's really all of, when you get into some of these other types where you're looking for high sulfite resistance, for example, we don't worry about that typically, at least in our part of the country, with things like sidewalk and stuff like that. But if we're pouring a wastewater treatment plant tank, for example, where we can expect that there's going to be high sulfates in the material that's held in those, then we want resistance to that. So that's why we would use a type 5 or 5A mix for that. This is a microscopic look to give you an idea of what those bubbles from air entrainment look like. Again, this is a pretty zoomed in shot, but as important as seeing what those are, also notice that they're pretty evenly distributed. So one of the things I referred to earlier when I was looking at that air content meter machine, right, that cost $1,200, $1,500, maybe they cost $1,800 now. There's a newer test that's come around into more common use in the last few years that takes that up a notch. It doesn't just measure the air content, in other words, the block amount of the raw amount of air that's in a unit volume, but it also gives you an estimation of how well distributed those air bubbles are, because that's key as well. It doesn't do you any good to have one big bubble off to the side. You really want to have a lot of small ones evenly spread out. So how do we do that? Well, again, we do that by placing the material as close to where we want it right from the, but we don't overly, vibrate the mix because the vibrator is going to beat the air out of it. We want to use come-alongs rather than garden rakes. And we want to use wood floats, magnesium floats, rather than steel trowels. So again, we want to put all of those best practices together so that we don't sacrifice the air that we spent money putting in the mix to begin with. So we talked about admixtures earlier, and again, this video drills into them just a little bit. And so you see some examples here of fly ash, silica fume is another one. I don't think I mentioned that one earlier, and slag. And they kind of all look similar to me after a while, because this is not what I do for a living, right? I don't run a batch plant, but I guarantee you that the people that run batch plants probably could spot these and pick them out and tell you what they are. I need a periodic chart of the elements to follow along. But generally these are going to give us various benefits that we're looking for in the mix, and they're designed very specifically into the mix. So again, it goes back to making sure that the material that rolls out on your job site is the material that you specified and that you designed and that you paid for. If you're looking for some of these specialty materials in your mix for very specific purposes, then you're not looking for some generic mix that was put together in the plant. You certainly, and that can happen just because the wrong truck went to the wrong job. It doesn't happen often, but it certainly can. It talks a little bit about some of the other components. So we want good hard concrete, right? We don't want concrete that's going to break up in the middle of this. Again, you have some similarities with asphalt. With asphalt, you can overroll the mix. You get to where the mix is cooled down too much and you're still rolling it. At that point, you're just breaking aggregate. And now you've got fractured aggregate with no bituminous binder attached to the front, and you're going to get potholes and early failures. Well, we want to make sure that the aggregate in our concrete can hold up to, the whole benefit of concrete, or the thing that we look to it most for, is that it's great in compression. Once we put it in place, we can put a lot of loading on it. Well, only if the internal materials can hold up to those stresses as well. So, placing the concrete, again, we want to put it, as near as we can early on. There may be, we use lots of methods to do this. So, we talked about, the ideal one, I suppose, is one where we are backing the concrete truck right up. We've got a relatively short chute, a couple of sections of chute, and it's going right where we want it. And then we can, screed it off and do our bit. Other places, we've got to use a concrete bucket and bucket it in, even using elephant trunks, as I alluded to earlier. Other times, we may have to use shuttle buggies or wheelbarrows to get back into spaces. That's less ideal because we're handling it more and we can create more segregation. With bridge decks and other kinds of larger projects, we oftentimes will use a concrete pump truck. Now, those are specifically designed to minimize the amount of segregation, but logically, you can imagine that that's a bit of a challenge. And so, but we're going to match our project. If we do our jobs well, if we have the proper equipment, and we know how to mitigate for any concerns, then we can place and consolidate the material well. Again, when we're vibrating so that we can consolidate the concrete, so in a case like this, you see the fellow on the right has got a vibrator. He's got a properly sized vibrator for the job, it looks like to me. And hopefully, if we saw a video of him doing this, or we're watching, what we would see, it certainly looks like it. He's got good form. It looks like he's taking that and sliding it vertically down into it. He's not throwing it out and dragging it through the concrete. That's a terrible practice. Don't let your concrete finishers do that. It should go directly in and out. It should be a relatively quick residence time, and you should move it around to different locations, particularly around the edges of forms, but also here where we're trying to make sure that we've got good distribution between what might very well be a couple of tight rebar mats in this, what looks like a bridge deck.
Matt,
Yeah.
we have a question. There's a
Yeah.
question that says, explain why steel trowels are used on pavement edges. We're told not to use steel as it kills the air.
Yeah, well, that's
Why steel trowels are used.
Yeah, that's a really good, that's a really good question, and that's a great practice. I don't generally see specifications that make that limitation. I think that that's ideal. And again, the reason for that is exactly what that questioner asked, which is or alluded to, because as opposed to magnesium and other materials, and this is not, I almost kind of understand why it is, but I can't explain it. It's a little bit beyond me. But the steel trowels will beat the air out of it. And again, when you think about when you're using those edging materials and things like that, you're doing it right at the sort of most exposed, most vulnerable part of the concrete. So they are very much to be avoided. Now, the most specifications that I'm familiar with don't outright prohibit them. They use words like they shall be minimized. They, mag floats are preferred, et cetera. Why is that? Well, because there's a practical reality that some people recognize that sometimes the mix is going to get a little bit away from you, and that you can make things happen as a finisher with a steel trowel that you have a harder time with a wood or mag float, for example. And you can debate that, but the idea is to minimize their use. Again, if you're working on internal concrete, you don't have that concern typically because you're not using air entrained concrete. But yeah, I mean, I think if you have a specification that is stronger in that regard, that's probably a good thing. I think the more you can encourage good behavior with the use, A, waiting until the bleed water comes off, and B, avoiding the use of steel tools, the better off you are. So just an example here, again, we probably, have some poor consolidation along the edge of the form here. Here, again, we're looking at these forensically. So we can speculate, but we don't always know. But here, several things come to mind. Perhaps the forms were removed too soon. Perhaps it was the wrong mix. Maybe too much water was added. Maybe it was poured in cold weather, very cold weather, and it hadn't been allowed to achieve 500 PSI before it froze, and it effectively spalled itself out, right? So, I mean, I'm riffing here a bit, right? I'm speculating because I don't know, but we do know what we can do is we say, well, we do have failures like this, and these are very hard to correct. That's to me the other part of this, where it is a pet peeve of mine, I suppose, that, well, this happened, but we made the concrete contractor go back in and reform it up and patch it, so it's okay. Well, no, it's not okay, because the patch is exactly that. It's a repair, and that's not what you paid for. You paid for top quality work by somebody that knew what they were doing and assured you that they were going to do it well. I don't want to pick on the contractors. That's not my purpose here. I've been a contractor. I didn't enjoy it, being criticized there either. But we've got to hold each other to the right standards here. And so, again, I can speculate about what happened, But what I'm confident of is that whatever we do to repair this at this point is probably going to be a compromise, and that's not what we paid for. You know, this is a crazy example. I don't know. They're clearly trying to remediate this. I really just cannot imagine that you could have any confidence in that wall patching this material. But so when I saw this, I don't know where this is. This is plucked off of the internet somewhere. That's nuts. That amount of material coming out of there. I really have to question whether they're going to be able to properly repair that. So again, the video from the Portland Cement or Portland Concrete Association goes on to talk again some of the things here. So, you know, some of the jargon that we use. So I've probably used the term bull float several times and not explained what that is. And I should be better than that, right? I shouldn't assume that everybody knows what that is. But so what you see here being used in both of these pictures are what we would commonly call a bull float. They most of the time are going to be magnesium bull floats, specifically for this period and so or purpose. And so what we've got here is hopefully we're conducting this work at a point where the bleed water has come off, or we've removed it from the surface if it was excessive and we need to do that. And now we're finishing the surface. And this is the first, you know, for the bulk part of the surface, we're going to use these bull floats, you know, to do the final finishing. And then we may use smaller tools around the edges or for the joints and things like that. It's really, really important that we not work that bleed water into the surface, because think about where, you know, where that water is going to go. It's not going down and evenly redistributing through the concrete mix. You know that it's going to reside in the upper quarter, I don't know, ½ inch of the paste. It's going to weaken that paste. It's going to weaken its adherence to the aggregate. And we're going to get exactly the kind of outcome that I showed you at the beginning of this workshop, where we've got, you know, scaling and mortar flaking and things like that. And we're just going to have, and again, it's not just that that concrete looks bad. That's not necessarily the big problem. You know, particularly when we're talking about roadways and things, who stops to look at it? So aesthetics isn't our concern. I guess that could go to rideability, but it's that now we've opened that area up for water to get down that concrete that much easier. Concrete is a porous material to begin with, but when we encourage mortar flaking and scaling, it just creates a more direct pathway into those more porous parts of the concrete, the more permeable parts of the concrete. So again, where we create joints, that ought to be established well before the job. The contractor ought to be given a direction as to where those go, either as an actual layout plan or as a, you know, every, you know, 10 feet, every whatever, so that it's designed in from the get-go. And we can, you know, we can form those, we can cut those as we have in this particular example. Again, joints can very much make the difference of the long-term durability of our concrete. Curing, getting back to that. So, so again, in this lower right, which was actually a foundation for a county administration building that I was building, you know, this was, these initial foundations were being done in relatively cool weather. And, you know, we said, that's fine. You know, under these circumstances, you can go ahead and do that, but you're going to have to take the steps of effectively, you know, not only using thermal blankets, but you see the propane tank there. We're actually requiring him to tent it and heat it with propane heaters to keep that atmosphere and make sure the ground around it isn't freezing overnight, while it comes up to its initial compressive strength, that it can resist the freeze thaw effects in the early stages of its development. But we can, again, we can cure in a lot of different ways. So, in the upper right, we're seeing a roadway train, the end of the roadway paving train, where, this machine is going through, it's doing the tining of the surface, which is the equivalent of with a sidewalk where we would broom the surface. And then it's applying that hood you see at the end is spraying a coat of curing compound. What's nice about that kind of setup is that you can get it sort of tuned in early on in the process and know that you're applying the kind of coverage that you're looking for. And then it's just a matter of monitoring it and making sure that the machinery doesn't get out of whack as you proceed. But you can get very good coverage of that. So lots of different ways that we can go about curing. Very, very critical that we get in early and do it correctly.
Matt?
Yes.
Matt?
Yeah.
It's a question. Why is mag float called mag float? Is it made from magnesium?
It's magnesium something or other. I guess, is it nah. See, I'm going to guess and I'm going to be wrong. I don't know. I want to say magnesium oxide, but I don't know. But it's magnesium in it. And again, I will embarrass myself if I try to explain too far down the pathway. But there is part of the reason why magnesium floats either don't draw air out of the surface or do it to a lesser degree. I'm not sure exactly which is true. Has to do with a chemical reaction in addition to other things. But beyond that, I will embarrass myself if I go too far with it. It's well established, the difference between mag floats or wood floats. Wood floats are again, very good for air entrained concrete as well. Wood floats require, they're a lot of folks call them old school, right? You got to be an old school craftsman to use a wood float well and get a good surface. But if somebody's using a wood float and coming out with a nice surface, chances are this is not their first rodeo. So just continuing with curing, again, don't sweat these charts too much. These are just the fact that this gets studied quite a bit, and this is not, there's no question that early and proper curing can have a very, very substantial effect on how early in the process we reach higher compressive strengths and what we ultimately achieve with it. The big thing is in how early it sort of steepens that early curve, if you want to think of it that way. And so these are just some charts of the age of the specimen versus the compressive strength, depending on different types of mix and different kinds of, whether you've moist cured it for long periods of time or continuously. Some of this, again, I've mentioned a lot of these as I've gone. I really do encourage you, if you're going to be doing this testing or you're going to be associated with it, I know these things cost a little bit of money, these standards. Any one of these standards might very well be 6, 7, 8, 9 pages and be $30. But you really do want to get your hands on it, because particularly if you're an owner or an inspector, then this enables you to look at the people who are doing this and say, either A, yes, they're doing it correctly, or no, you're taking shortcuts, and I want to make sure that the samples that I'm taking are credible, that I can depend on those results. So these are sort of the standard ones that at least go with the kind of routine testing that I've talked about. We're all probably familiar a little bit with concrete cylinders. We don't necessarily do this on the smaller jobs, but maybe that's a mistake, right? If we say, well, we don't do it on sidewalk. Well, okay, you're pouring 15 feet, 16 feet of sidewalk. Maybe you don't do it, that's fine. But if you are doing a substantial, series of sidewalk repairs or replacement throughout your town, for example, over the next several weeks, then maybe you snag a few random test specimens and get them to a lab and have them break as a way of making sure that, letting the contractor know that you asked for 3,000 PSI or 4,000 PSI concrete and you fully expect to get it. And of course, you can use this method early on, right? There are times where we say, well, I'm looking for 3,500 PSI concrete, but you can't put any construction loads on it until it's at 2,000 pounds. Well, then I'm going to want additional cylinders so that we can break those at, say, 7 days rather than 28 days and say, yep, you're good to go. You can now remove the forms. You can put construction loads on it, that type of thing. This was, I think, yeah, this lower right. So this was kind of interesting. In the structures lab at UD a couple of years ago, there were a group of staff and some faculty down as they smash these. When you break one of these cylinders, even though you know it's coming, it makes such a sharp sound that you'll about jump out of your shoes. So even when you're used to it and even when you know it's coming. But again, this is an example of the kind of specifications that you see where it's very important how these cylinders, you don't just dump plastic concrete into these test cylinders. They need to be put in there, for a 4-inch cylinder in 2 layers. They need to be rodded, a certain amount of times, et cetera. So all these are laid out in the test specifications that you're specifying. And you really want to know those, and you want to make sure that they're being adhered to, because it's the only way that you get consistent test results out of the back end. And otherwise, I would just argue that they're not meaningful. And this is, some examples, or, an example of, the center one of how typically a cylinder is going to break a little bit differently than what we see here. This was an unusual mix. I think those were mixes from the Guatemalan Engineers Without Border project, if I remember correctly. But in the upper right, you can also see that sometimes they're not test cylinders, they're test bars. So there's other ways that we can test these materials, because sometimes with something like that, even though concrete itself is good for compression, we are looking for a certain resistance to bending stresses as well, because it's reinforced concrete. And the lower right is a bath, right? Where if we're trying to mimic the circumstances under which the concrete out in the field is curing. And so that's what we're trying to reflect once these materials get to the lab as well. Sort of start to finish this out a little bit with some examples. So just an idea of some of the challenges and some of the component pieces that come in and sort of fight each other, right? So we have rebar for sure. In this right, one of the other terms that, probably a lot of us are familiar with, but some aren't. If you see that yellowish, I want to call it, material in the center there, first of all, the concrete material underneath it is what we call keyway. And so that's pretty common when we have multiple pours to create, for example, a retaining wall or head wall that's on a concrete gravity footer. That keyway helps the two components act more monolithically. The material above it is, again, of various terms, but I would call it water stop. So that was actually formed, the lower part of that is formed into that keyway, and then the upper part is going to be in the next section that's poured where we see the rebar. And so that material is going to minimize the amount of water transport that can go past that sort of cold break in the concrete. We have rebar here. Again, you can imagine there's going to be another wooden form on the left side of that rebar. It's going to be a fairly tight spot. So you can start to see that with some of these wall sections in particular, you have to get into some fairly tight places. And if you're moving concrete down 6, 8, 10 feet down into that form, then proper placement and consolidation becomes really, really key. This is probably a bridge deck. It sort of looks like it. This is pretty common. Back towards the lower right of the picture, you start to see sort of those slab edge treatments, whether they're stirrups or continuation bars and so on and so forth. You know, you can start to get a lot of rebar concentrated in one place. And so again, proper placement, proper consolidation without being at the expense of segregation is very important. Here is an example, a couple of things that come to mind. One is, so this is not uncommon when we're working with sidewalk slabs and things like that, to use, in lieu of rebar, to use wire mesh as reinforcement. But any kind of reinforcement needs to be at the place in the concrete where the tension is. Again, concrete is great for compression, but it's lousy if you take just a bar of concrete that you pour without any reinforcement and you put a bending force in the middle of it, it's going to crack pretty easily. Whereas that same slab of concrete, you could probably drive a truck over and over, and it wouldn't break if it was on the ground. We put the steel in there in the part of that slab that's going to be under tension. And so in the case I'm talking about, where you separate a bar, you know, a couple of feet apart by two supports, well, the tension fiber is going to be in the lower third of that cross section, and that's where we want the steel. So the problem is here, you know, sort of the classic thing is we go in, we pour a bunch of concrete on top of the wire mesh, and then we reach down in there and we sort of pull it up. Well, I may have some of it in the lower third, I may have some halfway up, some towards the top. It looks like a lot of this is just sitting on the ground. It's probably not, they would have been better off just not using wire mesh in this particular instance, because it looks to me like it's not going to be at a place in the slab where it can be effective at all. The other thing is I see a lot of sheen on here, which suggests to me that there's a lot of bleed water here. That's fine, and you do get that. My immediate concern would be I'd want to make sure that they're not in there doing any kind of excessive finishing before that bleed water has a chance to evaporate off. Another example where we, can have a lot of rebar in a fairly tight place and a fairly mass pour. If we were doing this may or may not be considered a mass pour, depending on your specifications. I'd need to know more about it. But in a mass pour where you've got so much volume and the heat just can't get out of there, you can really have adverse effects. So in a mass pour, oftentimes we even have tubes with water or glycol or something like that going through it, where we'll actually be trying to cool down the inner core of this so that we get a more even distribution of the heat of hydration. But even with something like this, we're going through a lot of rebar cages, and we want to make sure that we're very deliberate about how we place that concrete and how we consolidate it. With that, again, you just sort of see the challenge of a pour like this. The finish. So this is finishing that's associated with the edge of a expansion slab, I think, or not expansion slab, approach slab for a bridge, if I remember correctly. And again, he's just getting in there and he's going to leave the area around that rebar cage. No, it can't be that. I'm not sure what this is. I spoke too soon on that as to what it was. But in any event, the point of this picture is that rebar cage is a continuation cage for something that's going to go up above it. That might be in a large curb section or something like that. And he's going to leave that rough in there so that we can have some good bonding between that section and the next layer of concrete. But then he's finishing outside of that envelope. Again, they talk about floating and finishing, bleed water, the whole, sort of cardinal rule. This is one of the effects we can have, this so-called glazing that we can have, where if we're working bleed water into the surface as well, in addition to, scaling and things like that. I have this in twice. It's like a bonus shot. Again, will this finish well? If they allow the bleed water to come off, it probably will. But again, real rebar problems here. Here in this kind of case, you see probably some mix of scaling and mortar flaking. You know, it's pretty clear that there were some water issues with this. They applied too much water to the surface. Maybe they didn't cure it well or early enough. But this is just, you know, this is a relatively new concrete surface, and it's already seriously distressed. It's just not acceptable, and we really just shouldn't tolerate it as owners of projects. We need to take steps to make sure that we get, again, anybody can have a bad job, right? But if we're seeing this on any consistent basis, we should certainly just look around us and say, well, others are doing better than this. Why aren't we? Right? They talk a little bit about, you know, some of those QC tests. It's interesting. The lower right there is the Federal Highway Administration Mobile Concrete Lab. They have a small team of 2 or 3 people. They take this all over the country. We've had it at our own roadway management conference that the Mid-Atlantic LTAP Centers put on every year. They walk through and show proper material testing techniques and some of the cutting edge technologies that are coming out with management of good quality concrete. So if you get a chance to be around those, if they come to a town near you, a job near you, go out and spend a few minutes and have a look, because they're very, very instructive. And so I've run the course of the materials. So, you know, we're doing okay on time. I guess what I'd ask a couple of things. One is, Rusty and Sandy, what did we hear in the chat box? Hopefully we heard some things about that second poll question about what QA testing was used. Did we get some results on that?
Yeah, we got a lot of results, Matt. Most people saying all, some saying it's subcontracted out, but a lot of them saying that they do all of those tests. And on the first poll, got a lot of no's, not sure's, no, but they like the idea, things like that. Just a few, very, very few yeses. And we have one question very early on about how does linseed oil help with scaling?
Oh, I don't know. I don't know. That's an interesting question. I know linseed oil for woodworking. I don't know. I'm sorry, I can't answer that. I'm not familiar with it being used routinely, but again, I mean, one of the things that I'm always conscious of, particularly when I know that there's folks from other parts of the country, you know, you get into other environments and, you know, even other materials, right? I mean, you're using different kinds of aggregate if you're in North Dakota or California than we would have here on the East Coast or our part of the East Coast, for example. And so things that, you know, we don't use here because of the indigenous materials we use, you might use there. That's interesting. If whoever commented on that wants to come off mute and talk about their experience with it, that'd be interesting.
Yeah, Matt, that was me, Mike. One of my colleagues at work here is an old school, he was an old school public works engineer. He headed up the public works department out in Omaha back in the late 70s, early 80s, I believe. And that was one of the big things he speaks of, you know, quite a bit about. Even here, he talks about applying boiled linseed oil basically about the time you're finishing flat work like this, sidewalks in particular. I mean, it sounds like some of the newer compounds are putting down to help sealants, you know, with sealants and things like that. We see a lot of specs on, you know, users like Wawa, Royal Farms, the gas station folks, you know, they want to apply certain things to their concrete because of the materials they have on their slabs.
Right.
You know, from selling their product. But this, I mean, the boiled linseed oil just kind of seemed like it was an old school thing. I've heard of it from back when I was a kid. I just wasn't sure how much it's been applied here.
I'm not used to it. So that's really, as they say, that's a thought that'll fester, right? I'll want to go dig into that a little bit now. And again, it might very well make sense because part of what you're trying to do with regular curing compound is you're looking to leave some kind of a residue on the surface that temporarily seals off the surface. And so curing compound, anywhere from 6 months to a year or so afterwards, depending on traffic across it, it's all gone from the surface. It gets rubbed off because it's basically just a waxy residue, and it's designed to do that. So the boiled linseed could very well be doing the same thing. Yeah, I'll have to dig into that. I appreciate that. That's
Sure.
something to think about. You know, and all these things come down, you know, all of it comes down to cost, right? If you have two different methods you could use, you know, I'm a big fan from an owner's perspective of giving the contractor license to use either one. I say either one of them done properly will be effective. So you pick whichever one you like, that's fine. And so I don't like being very prescriptive. Typically larger agencies are getting away from prescriptive specifications and getting more into performance standards, which I think is good. It gives the contractor the ability to play to their strength. They may say, you know, look, you know, the kinds of jobs that we're doing, we like to do it with wet burlap. And I mean, that, you know, when I was in heavy construction early in my career, we did a lot of bridge decks and things like that. And we did wet burlap and kept it wet for 7 to 14 days, depending on the project. And, you know, that's very labor intensive, but if you have the right labor structure, that can be fine. And, you know, I think part of it was we were just very comfortable with that approach and that technique at that time. But so yeah, there's lots of ways that you can do that as well. Quickly on the topic of testing, I'll come back. I'm glad to hear and now see those responses. You know, there's lots of ways you can do this, and particularly, you know, I'm quite confident that on today's call, there's lots of, you know, local agencies, smaller agencies, be it municipalities, county governments, et cetera, and, you know, or even, you know, other small owners of projects. And, you know, there's a tendency to say, I mean, I know, you know, I was public works director for Cecil County, Maryland, here at the head of the Chesapeake Bay, and, you know, a small rural county. And the view when I arrived, I said, you know, where's our testing equipment? And they said, well, you know, we have an old beat up slump cone. And I looked at it and I said, okay, well, that's not really working for me. You know, we're building an $8 million project here. I think we can afford a $150 slope cone. Let's get a new one of those. And I said, where's our calibration meter? And they said, well, we have one, but it hasn't been calibrated in you know, 10 years. And so we don't use it. I said, well, then let's get it calibrated. You know, well, you know, the last guy wouldn't let us pay for that. I said, well, the last guy's gone. Let me introduce myself. We're going to do things the correct way here, which is not to say that you do it all willy-nilly, right? Again, I mean, am I going to go out and I'm doing, you know, 20 feet of sidewalk and I'm going to pop test cylinders? Probably not, no. But you know, I mean, that would be pretty unusual behavior, I would think. On the other hand, you know, if I'm doing a whole series of that, I probably would like to get some representative samples here and there, just for my own edification, to make sure that I'm getting the mixes are working out like I expected, but also to sort of send a message to the contractor and the batch plant that, look, I'm watching a little bit. I don't have to do that myself as my agency. I mean, again, you know, where I was in public works, I was lucky enough to have, you know, some inspectors who knew what they were doing and could do that well and were serious about what they did. And so they went about. But as an alternative to that, I could have hired a consultant group, you know, a testing firm to come in and do that for me in the same way that I would bring in a testing firm to do, you know, Troxler tests, you know, with a nuke gauge on my asphalt. So there's a lot of different ways where, you know, we can do it. And obviously you need to, it needs to be reflective of the magnitude of the job you're doing. You don't want to spend, you know, $100,000 to test $50,000 worth of construction work. That would be pretty silly, but, so you want to balance it, but I really do encourage, you know, be involved in some quality assurance and quality control issues. Over the long term, it will give you better results, I think. But insist that it be done correctly. Are there, I know we're getting close to time. Are there any other questions that have come up?
Nope,
Okay.
that looks like it, Matt.
Okay. Well, thanks so much for joining us today. I hope you've gotten a little bit of something out of it. And again, if you run into questions, you've got our contact information here, and you can access these slides. You know, so reach out to us if we can be of help. Thanks so much for joining us, and we'll bid you all a good day.